Yes, welcome everybody. I'm very happy to introduce Frauke Liers today. So she's a full professor at the Friedrich-Alexander-Universität Erlangen-Nürnberg. I didn't find the English version of this university, but so it's...
It is the German. The German is correct.
Okay, yeah, okay, that's what I thought.
Corporate identity.
Yeah, so she was studied mathematics at the University of Cologne, and very early in her career, she received the very prestigious Emmy Noether funding for a junior research group from the German Research Association. And yeah, she's well known for work in optimization under uncertainty, including robust optimization, of course, related to combinatorial mixed integer problems, also nonlinear problems, and recently also integrating data-driven approaches. She has coordinated several larger projects, for example, the European Graduate School Minoa, where we talked about. And yeah, I'm very happy to have her here, and please, okay.
Yeah, Janis, thank you very much. And also thanks a lot to Ahmad Reza. I think that's really a great initiative that you have, that you have this regular online seminar. Now I try sharing the screen, and I hope it is. Yeah, is it okay?
Yes, perfect.
Okay, thank you very much. Yeah, so thanks for this kind introduction and also for the invitation. I would like to explain about a recent project that we had about data-driven distributional robustness. And we are thinking of it that we have a planning process that somehow repeats over time. On the other hand, there are always, of course, some uncertainties, disturbances. So not every day or every hour or so is the same, but there are these uncertainties, and we would like to take robust decisions. And we would like to learn, I put it in quotations, the relevant uncertainties together with then the robust decisions. And also, I mean, you see the group of people who contributed to that. Yeah, we were for a while not sure how was a good model, how was a natural solution approach. So many people contributed, and then it turned out that basically there were in particular two main drivers of this work. One is Kevin Eigner, also from FAU, and Kati K. Sharma from Berlin. Yeah, okay. And I would like to first explain the motivation where we started to work on this data-driven distributional robustness. And that was a very different thing. And that was a quite applied project that I would like to explain. And then I will explain the motivation for the more theoretical and algorithmic work that is then this data-driven distributional robustness over time. So this applied project was about delay minimization and ambulance logistics, where we were working together with the Integrated Control Center in Nuremberg in Germany. And we wanted to integrate the ad hoc ambulance transports into the plannable ones. And it turns out that it's the largest integrated control center in Germany. So they have something like 30,000 ambulance transports, and only something like 30% can be planned or come in ad hoc, whereas all the rest could be planned, say, a day before. And they have something like 44 cars. And it turns also out that some of these requests can be shifted, but some, in particular, those ad hoc transports, they are urgent. They are typically not known beforehand. Typically, these are intensive transports then, yeah, and they have to take place now. Some others can be shifted. So in general, that's a vehicle routing problem with time windows under uncertainty, because sometimes there are some delays or some hospital can only release a patient later than thought. And these time windows, some of them are hard and some others are soft time windows. And now the question was how to set up some scheduling approach. And for this, we did first some algorithm engineering for the optimized routing. Yeah, where we did the following. They have something like all the data of all the ambulances of the last 10 years. Yeah, so, and we said, okay, I mean, we do some data analysis of that. Then we find out where there are typical requests, at what time of day and where. And we would like to plan them in as some dummy requests that may manifest themselves, and the others that are known beforehand. For example, some dialysis transports, or if you have to transport somebody from hospital A to hospital B, these are then the known transports, together with those from the data analysis. We integrate in the planning phase, say a day ahead, such that it's a vehicle routing problem with the time windows. We solve it, we plan with these dummy requests, and that takes place beforehand. And then we said, okay, now in the operative planning, we thought we are at the integrated control center, and we do the vehicle routing for the planned requests, together with those then requests that then come in ad hoc. Maybe these are the dummy requests, maybe these are others. Yeah? And we compared ourselves to something that we call a simulated reality, where we simulate how the control center does the planning. Yeah? And then we found that doing the dummy requests together with the known transport on historical data, there's a very nice average daily improvement in the total delay and also in the maximum delay. And yeah, then we did some further algorithm engineering things, and also we looked into extensions to the COVID-19 pandemic, and found out that one could also do separate pools, which is what they liked a lot. Yeah, one car fleet for the patients with known infections, the others are transported with the complement then. Yeah, and here's some visualization platform. So the integrated control center was quite happy with that result. And starting from this, we thought, okay, what can we do more? Yeah? I mean, what is basically the characteristics of this project? And then we said, suppose we start with basically zero amount of data about where will requests come in, and we do some planning. Now we are in the evening, and we then see, what was the number of requests, where and when? Could we not learn from what actually has happened when we do the planning for the next day? So on a meta level, we abstracted away from everything that we saw about ambulances and all these things, and asked ourselves, how could we learn the uncertainty and the protection over time if we have a repeated process that then repeats, yeah? Say day after day again, or hour after hour again. So, and this is then what resulted in this recent project that I now will talk about. So suppose you do not have any knowledge about the history and you would like to have a robust protection. So there is no other chance than to do a strict robust protection. Now, if you learn more and more about, what actually has happened, you would like to more and more trust the stochastic solution. So naturally, you arrive at something that is distributionally robustness. And now the question is, what should be the model for the uncertainty, that you learn more and more over time? And the way we formulated the problem is as follows. Very abstractly and very generally, suppose you're optimizing over some ZX with, we just said, an uncertain objective, and also motivated from the control center application, we said we have a discrete probability distribution. Yeah? So we have a discrete random vector with finitely many realizations from S1 to S cardinality of S, and the true probability vector P star. Yeah, that would that would then be this stochastic solution here. And this stochastic problem then just says, okay, just minimize or give me or solve the expected value problem. Yeah, where we then, because we have a discrete random vector, just have this finite sum of our uncertain objective, summed up with this true probability vector. So that's the standard stochastic problem. Now, you say, okay, you are the integrated control center. You don't really know what your true probability distribution P star is. So in practice, it's unknown or uncertain. Now we say, okay, I mean, we want to be protected against uncertain probability distributions. We may have already some good knowledge about it, but not fully. Yeah? So what we then do in general is this distributionally robust optimization approach, where we say, okay, we define some ambiguity set, yeah, where our uncertain probability distributions reside in. And then we just solve the robust optimization problem. We want to determine the best possible decisions X, maybe the best possible schedulings, even in the worst case of the realization of the uncertainty, we want to be best possible. And in the beginning, where we do not know anything about the historical data, there's no other chance than to say, well, our ambiguity set is simply the probability simplex. In the sense, every probability distribution is possible. Yeah? So, and now that would be the start of our optimization approach. And now we would say, okay, how can we somehow move from this situation where we do not know anything about the history? So that would be then the full robust optimization problem. Yeah, we solve our DRO problem over the full probability simplex. How can we move until that we basically have the full knowledge about our true probability distribution that we have to assume is there? Yeah? So that basically our ambiguity set then only contains this one single P star distribution. So there is already some knowledge and some literature, but they are usually tackling the stationary case, yeah, where you do not really learn over time, but still, I mean, what would you want to do at that point? You would like to say, you want to do data-driven distributionally robust optimization, where you say you construct n many observations from which you construct an ambiguity set such that your true probability distribution is contained in this ambiguity set Pn, at least with some confidence, and that is then, of course, contained in the probability simplex. And then in some stochastic sense, you would like to guarantee that this ambiguity set Pn converges to this full, this P star that only contains the true probability. And you always solve then the distributionally robust optimization problem, where you have, your ambiguity set Pn constructed out of your n observations. And then the idea is you somehow want to shrink this ambiguity set iteratively such that this data-driven DRO that I just mentioned is always satisfied. So now in data-driven distributionally robust optimization, there's a lot of literature, and I only mention a few things, but of course there's much more. In general, it's important to guarantee that you have uncertainty or ambiguity sets that are as small as possible, but still as large as necessary to guarantee some solution quality. So for this stationary case, yeah, you have, for example, some work where they constructed ambiguity sets from hypothesis tests. Or what is very important for us is this work here, where Esfahani and Kuhn gave some reformulation for Wasserstein ambiguity sets. Yeah, and then also if you, for example, know a lot about your distribution, but you say maybe the first moments are uncertain, then you can do some reformulations for moment-based sets. But as I said, there's a lot more that is out there. Then let's see how we do it if we want to now include this time dimension in it. What we say, I mean, is we have to now answer the question, how should we construct our ambiguity sets? Yeah, so that iteratively you observe more, say after you have done your vehicle routing in the evening, you then find out what were the requests during the day. and then you would like to adapt your ambiguity set in that evening, yeah, for the next day. And we thought about several different possibilities how to do this. So the algorithmically easiest is to intersect your probability simplex with confidence intervals, which means you just say, okay, the probability simplex is not, is not completely relevant. I can somehow show that with some predefined confidence probability, my true probability distribution is contained between lower and upper bounds. Yeah, and these lower and upper bounds have to be constructed however they are known. For example, if we have the multinomial distribution in mind, yeah, then it's known how they can be constructed. Basically, these confidence intervals in that case say something like you take the maximum likelihood estimator, and from that you go a little bit to the left and to the right, and this going to the left and to the right is just taking the marginals of the standard distribution. Yeah, so that's known, and it's also known that if you have n observations, that then the confidence sets shrink with O of 1 over square root of n. Yeah, if you use a fixed confidence. So in principle, we now know how we could shrink our ambiguity sets if we have a new observation. Yeah? We just use these confidence probabilities. Suppose you now want to use it in our DRO problem. So how do we do it? We now are not anymore in the position that we have to optimize over the full probability simplex, but we can now intersect it with these confidence intervals, upper and lower bounds. From an optimization point of view, that's very nice, yeah, because the only thing that happens is that if you look at this inner optimization problem for the adversary that optimizes over the ambiguity set, this is a linear optimization problem, yeah, where you then say, you are in the probability simplex, you have intersected with upper and lower bounds. You can simply dualize this inner maximization problem and then apply the standard robust optimization approach and write down a reformulation where you replace the maximization that is here in the inner with a dual LP for this discrete probability distribution, and then you end up with this reformulation that is closely related to the nominal problem, but of course it has the dual vectors here, yeah, for the optimization over the ambiguity set. But if you assume that optimizing with your function f was algorithmically tractable, then it's also reasonable to assume that this optimization problem here remains algorithmically tractable. Yeah. One, however, has to take care of the fact that now for each dimension you are in your probability simplex, you have to add one constraint. Yeah, and you also get these two dual vectors for any dimension. So that can go quite large and can increase drastically. Still, in general, you can say it's algorithmically tractable. We also looked into other ambiguity sets, for example, ellipsoidal ambiguity sets, because they are motivated, for example, from L2-based norms or also from kernel matrices, yeah, where you say you are around some empirical distribution and you allow in your ambiguity set everything that is around, where you say this around has to be all probability distributions that are in some norm near to your empirical distribution. And it's also known that if you want to have this confidence property, so you say that your true probability distribution should be contained in your ambiguity set in the nth round should be at least 1 minus some value of delta. Then it's known that if you have say that just an L2 based norm, yeah, then this should be the radius of your ambiguity set. Or if you allow a kernel matrix and a kernel metric here, then this should be the radius of your ambiguity set. So that's also doable. And now if we go back to our reformulation, then it's also no problem, yeah, to apply the duality for the inner maximization problem where you optimize over the ambiguity set. Namely, you can say, okay, that's simply a conic optimization problem. And you can also reformulate it and yeah, use it here such that using standard robust optimization ideas, replacing the inner optimization with its dual, you also have something that you could say is algorithmically tractable if your original problem with the function f is algorithmically tractable. Nevertheless, it can become computationally expensive because, yeah, also in particular because of the size of this script asset. So you may want to refrain from solving this reformulation in practice. Nevertheless, it is already a reasonable and feasible way to go. Yeah? Namely, how would now our optimization approach look like? Our data-driven distributionally robust optimization approach over time now starts with the following setting. We have to solve a problem repeatedly over time, over t rounds. There's new incoming data in each round, and you would like to incorporate this new data in the solution process. Our robust solutions should learn, yeah, from the uncertainty and should become less conservative as the knowledge about the uncertainty increases. And if we go to infinitely many iterations, we have perfect knowledge of the uncertainty and we end up with only the true probability distribution P star. So now how does it work? The algorithm is almost there, at least this first algorithm. Yeah? Namely, it looks as follows. We have our time-dependent ambiguity sets. Yeah? So in round T, we either have the probability simplex intersected with the corresponding confidence intervals, or we have it intersected with these conic norms. And such that with the correct confidence, our true probability distribution is contained in, yeah, what I just explained. So what we first do is we initialize our starting point with a full probability simplex. We always do in each time step the following. We compute the distributionally robust optimization problem with the corresponding ambiguity set, yeah. Then we observe what actually was the realization of the uncertainty, and we have to shrink our ambiguity set appropriately, yeah, depending on what we do. I mean, what kind of ambiguity set we have. And we give as an input a final overall confidence with which we would like to have that P star is contained in our ambiguity sets. And in order to reach this delta confidence, in each step, we have to do the confidence update with this, which, so it's 1 minus 6 delta divided by, you see it here, the formula, because writing down the details, that means that then actually it's true that with the probability at least 1 minus delta, the true probability distribution is actually contained in the intersection of all the ambiguity sets. Yeah, so that's a technical formula. So that's the algorithm. Sorry?
I have a very short question. So your uncertainty set, the uncertainty set S is not growing over time, so you don't get new scenarios in each time period?
You just say you are in the probability simplex and you always observe a new realization, yeah? So the way we here. Yeah, we just say we have a discrete random vector with in S many dimensions, and every day you find out what was the new realization that day. And we always say we have basically in the beginning, we have everything that is possible is just contained in our probability simplex. And now we would like to cut away the unnecessary edges, so to say, or the unnecessary parts of our probability simplex.
Okay, so at the
it's
beginning,
more the other way around. We don't gain more and more scenarios. It's just we first assume everything is possible, and then we basically cut away the things where we believe that is not necessary.
okay, yeah, thank you.
Yeah, you're welcome. So where have I been? So yeah, so this is about the shrinking in each set. So now the question is, I mean, what can we say about that approach? Yeah, in each iteration, we gain more information, so we can shrink our ambiguity set appropriately. And what can we say? So the way we shrink, actually we can show that we do converge to the stochastic optimum for infinitely many iterations, so that we can show. And we also can show that if we have a compact feasible set and a continuous function, then any accumulation point of the sequence of the solutions that we generate is almost surely an optimal solution to the stochastic optimum or stochastic optimization problem. And it's very nice that this work here tells us basically the steps that we can follow. I have to say that this work by Esfahani and Kuhn, they look into the stationary version of the problem. Yeah, so it's a different problem that they study. Nevertheless, the theorem that they have is closely related to the theorem that we can derive. And in fact, the proofs look very similar. Yeah, so we could follow their ideas. We also had to show that the way we shrink our ambiguity sets over time leaves us with the fact that we are converging to the true probability distribution with probability 1. Yeah, so this theorem is we had to do the proofs ourselves. Nevertheless, it was a great help to have this work here, because we could follow the proof strategy that is outlined there. So in theory, we already have a correct method. Nevertheless, let me come back to the fact that if we do the reformulated optimization problem and solve it as a reformulated task, that can really be computationally expensive. And so we thought, okay, we have a nice theory, so in principle it works. Nevertheless, the question is, can we do it algorithmically better than simply, observe a new realization of the uncertainty, shrink the ambiguity set, do the reformulation of our DRO problem again, and so on. That works and gives us the true stochastic optimization solution finally. Nevertheless, it is time consuming. So we thought about a different approach via online learning. And this has been used, online robust optimization has been used in robust optimization already. For example, you may know this work by Benthal and co-authors about the Oracle-based min-max robustness, where they used the analysis of online optimization for their algorithm. Then Pokuta and Xu looked into general conditions when such learning algorithms converge to the true thing. Then there is some recent work where they do Bayesian optimization also with online learning, but always, as I said, in the stationary case. Yeah. So, and now let's see how we can do it in our setting. what we want to do is, instead of having in each round to solve a fully reformulated DRO problem, we say, well, we do some gradient descent approach, where we say, we have two players. One player is the adversary and tries to give us worse uncertainty realizations, and the optimization player then has to solve a stochastic optimization problem. Yeah? For this stochastic optimization problem, the uncertainty player gives us a new uncertainty realization, and so on. And then we said, okay, now we want to restrict the effort even further and let the adversary not really generating the worst case realization of the uncertainty, but we only allow it to go one step towards worse uncertainties. So the idea is, we are the uncertainty player. We go one step towards worse uncertainty realizations. We let the new X player optimize for this probability distribution, the stochastic optimization problem, for which then the adversary goes one step in uncertainty space, and so on. So it's a very asymmetric thing. Yeah, the uncertainty player only goes one step, whereas the optimization player always solves the full problem to optimality. And as we are having our ambiguity sets, it may also be necessary to do a projection in the uncertainty to to have a feasible uncertainty realization. So how does it now work? The algorithm with the online learning. So we again initialize our problem that we have some uncertainty realization together with the corresponding initial solution. Now for each round, we do some gradient descent step or one gradient descent step and project it such that we get something that is feasible. For this uncertainty realization, our feasibility or optimality player has to solve the stochastic optimization problem. Yeah? Then we observe what has actually happened. So for example, now we are at the evening of the integrated control center, and we observe what were the requests that day. We shrink our ambiguity set with this confidence. Then we do the next round. Yeah? For the new ambiguity set, we do a gradient descent step together with a projection, for which we then compute a stochastic solution. Yeah? We then observe the data, what has actually happened, and iterate until we output the sequence of solutions that we have. Now the question is, does that work? Yes, it works. It also converges to the stochastic optimization problem, and it avoids solving the fully reformulated problems in each iteration, although we do much less work. And now the question is, how quickly does it converge? And this took us a while to find this dynamic background. And it works as follows. Under some conditions, such as our objective function has to be uniformly bounded, so that means it has to be bounded by some value of g, regardless of what x and what uncertainty we have. Then we have a certain step size, that contains some function h of t that we have to speak about later. And on a meta level, that function h of t is basically something like the path length that we have in the uncertainty space. Yeah? And then if we do this step length, then we can show that if we do the correct confidence update that we had, then we have, with a certain probability of at least 1 minus delta, that our cost that we observe in round T minus the best DRO solution that we would have had in that round. Yeah. So the difference between the solution that we play and the true DRO optimum is bounded above by something that goes with the square root of 1 over t. It has this function h of t in the nominator, and something that also that goes to 0 with t iterations going to infinity. What does that now mean in more detail? Here I say this is the cost that our solution would have observed. We play the xt, and we say, okay, what is our cost in the worst case? Well, our cost in the worst case is achieved when the adversary really takes this ambiguity set in that iteration t and maximizes it so that it makes it really as bad as it can. So that's our cost. And then we average over all iterations and take the mean. So we take 1 over number of iterations and we sum up all the differences between our solution and the best possible solution. And now we say, okay, this is bounded by this value here. Now the question is, what is this value? I told you this h of t appears here. This is basically the sum of all the path lengths that we have. And I will tell you soon that this h of t is actually better than square root of t. So that square root h of t, and that there is a sublinear convergence. So basically, that means if we already have that h of t is better than t, then we know that this square root of something goes to 0 over time. So now let's look into what is this h of t value. And without going into detail of the different formula here, we calculated h of t for the confidence intervals, then for the kernel-based ambiguity sets, and for L2-based ambiguity sets. And it always turns out that the sum of all the path length is bounded by the logarithm t, or log square of t. So if we go back to our regret bound, then we basically have square root of log t divided by t. So that is going to 0 if t goes to infinity. And then one can also relate it to the, if you know the analysis of online gradient descent, that has 1 over square root of t. And as we have shrinking ambiguity sets, this 1 over square root of t cannot be obtained. And you have this additional factor h of t in the nominator. So let's come then to the numerical results. For some instances, what we did was we took the smallest MIP-lib instances and also the smallest quadratic QIP-lib instances and checked how does our online robust solution develop over the number of rounds. And we took here as a prototypical instance this blend 2 instance. And you can see here that basically the green thing here is the stochastic solution. And we are, with our online robust solutions, we are, converging. And here we are also, I mean, there is still some difference, but if you allow more iterations, then you are converging there. Then here, let's see what turns out with the different ambiguity sets. Here again, we have, this blend 2 instance. Here's our stochastic solution. We should attain it eventually. And we choose different ambiguity sets, both the interval, kernel, and the L2 norm. And it turns out that this interval is quickest by always with going closer to the stochastic solution. Then how about the numerical results, running times? As we can avoid the effort of solving always the reformulation and only in our gradient descent approach do in only one step in the uncertainty space, we are also much faster. So this is most remarkable, I would say, in the mixed integer QP lib, where we here doing the reformulation always end up at some time limit, or at least in one instance, our method can nicely solve the problem, much quicker. And so we are much faster than the reformulation. And we also looked into robust network design instances that I don't have to go into detail. It's about how to set up min-cost network expansion such that you can route all flow scenarios that you have. And also here we see a nice convergence to the stochastic solution that is here over the rounds. And I would like, and also for the running time, we see that we are really quick, within 5 seconds, whereas you have here more than 1,000 seconds. And I would like to explain or show some computational results that I like a lot, namely with the Chicago instance. You have, I mean, we took that instance and then we made up uncertain travel times, at least to a certain extent. We made up our true probability distribution, P star, and it turns out that the solution adapts in these rounds, in round 1, 349, 80, 60, and 3,000 something. And I would like to show this is then the true stochastic solution. Suppose you want to go from here to there. And in the beginning, you're quite okay doing here, but wherever there is something red, you are wrong. And then you update in round 1 and you go like this, and you are closer and closer to the true stochastic solution. Here you're already fine. Here you still have some deviation, but also after these rounds, you have obtained the true stochastic solution. So as a conclusion, we have thought about a new framework for distributionally robust optimization over time in combination with online learning in order to be more efficient than always solving the reformulation. It is a method of learning the uncertainty together with robust solutions over time. We integrate new information without resolving the full DRO problem. And from my point of view, there are many potential extensions possible. This is just a first version of this learning over time. And we have, in general, quite weak assumptions on F. I always said, we don't say a lot. We simply say the stochastic problem has to be tractable because in our online learning, we have to solve it many iterations. And what we currently do is we try to apply also some scenario reduction. And I think, the motivation came from the integrated control center. And the next step, I showed you some results for the shortest path in Chicago. And of course, what is yet missing is to apply this approach for the real application in the integrated control center. And I also think there are many other questions in that area. So where you want to integrate data and forecast and learn over time your robust decisions. And with this, I want to conclude what I wanted to say. So thanks for your attention.